class notes, a couple of keys here. Really, this whole first page I want to talk about, it's just notes, it's no problems or anything. It's stuff you already know. But on the AP exam, okay, wait, you guys are sitting right in front of me. How come you're just not getting
We were going to read up.
Students will be expected to determine which model is most appropriate given a set of data. So we're going to talk about that today, but we've already talked about it. Here are the main types of equations that we've been talking about. So, linear model, there's a picture of it. There's a data table. And what do we know about linear models? You can get that after school, sweetheart. What do we know about linear models? The rate of change is constant. Now, let's be real. In a set of data that's actually gathered, are those differences actually going to all be exactly the same? No. So notice he says, when the data reveals a relatively constant rate of change. Do not expect a random data set to have, everything is 3.2, 3.2, 3.2. No. But if it's relatively the same, if you sketch it and it looks like a line, then you'll use a linear model. Now, when do we use a quadratic model? Well, what happens when we plot the ordered pairs? They are going to have a parabola shape, roughly, right? Up or down. What happens with the data table? What happens with the differences? They are increasing or decreasing by a constant rate, so they're linear, in other words. So the differences might be 2, 4, 6, 8. That means you have a quadratic model. And then what happens in an exponential model? Well, look at the picture. You know what an exponential looks like? And what happens to the differences? They are proportional, right? And of course, everything I just said hinges on what? The input values are equal with intervals, right? Okay, so now we have 4 examples, and you are going to determine which model is most appropriate. So with your friend, figure out whether these are linear, quadratic, or exponential. Example 1. Okay, what do you think? Linear, everybody good with that? Linear model? How about D? Quadratic model, what happened on that one? It signaled you in it was gonna be quadratic. It went up and came down? What about C? Exponential, everybody okay with that? And what about D? Another exponential? No issues, everybody okay? Was there any difference between the exponential in C and the exponential in D?
Yeah.
The first one was decay, and the other one was growth. You know what that is. All right, then he's got a little bit of a discussion about residuals, which we've already talked about. What is a residual? What do we mean by a residual? How far away from the actual value, the predicted value is from the model? And to calculate that number, we always do the actual minus the predicted, right? And the predicted is the value you get from the model, okay? All right, so here we go, example 2. We've seen, I don't know if it's these exact numbers, but we've seen an example like this before. So the rate of newborn babies can be modeled by a linear function, okay? Use the regression capabilities of your calculator to find a linear model, and be careful of the form y equals a plus bx. I don't know if you've noticed, but in your stat calc menu, there are actually 2 linear regressions. One is ax plus b, and the other one is a plus bx. So he wants you to use this a plus bx model. So get your calculators out, let's put in this data, stat edit, put it in. And make sure when you do your stat calc that you are storing your equation. I want you to get in the habit of that so you can graph that equation. If you have forgotten how to do that, ask your neighbor or you guys with the new calculators, it's easy. Your ones is a little harder.
No, but no.
Okay, did we get an equation, anybody?
Yes.
What's your equation look like? Y equals
3.34
3.34
plus 0.8.
0.8x. Perfect. Everybody get that? All right, now, here, I want us to practice this, guys. This is a simple little equation. So when the next problem says, you know, use your model to find the weight, or find the weight when the baby is 2.5 months old, this is a super simple equation. You know they usually don't come out that way. They usually come out with about 15 decimal places, right? So I want you to practice letting your calculator plug it in. So remember, all you need to do is get your y variable, and then put parentheses, whatever number it is, 2.5. I know you can get it by plugging it in, but I want you to practice this on your calculator. Did you get 5.34?
Yeah.
So what would that be unit-wise? That's 5.34
KG.
kgs. Yep, kilograms. Okay, so did everybody do it the way I asked?
Can you hold that?
Yep. Did you store your equation? Well, we need to store it so that it knows what it's plugging into. Okay. Okay. Now, those of you that have it in and have done that task, would you do C? The actual weight of the baby was 5.5. So what is the residual? And did the model under or overestimate the weight of the baby? So how do we find the residual? Actual, so the actual weight of the baby was 5.5 minus the predicted, which you calculated, or somebody calculated to be 5.34. So what's your residual? 0.16, which means the model underestimated by 0.16 kilograms. Your residual is going to have a unit on it, just like, you know, everything else. Everybody okay? Now, all of that's kind of old news. Some of us, I think, need to refresh a little bit on that. But what we haven't talked about is now this next box here. Using a residual plot to check the appropriateness of a model. If a model for a given set of data is appropriate, the residual plot should appear without pattern. Okay, that's important because you're going to have to determine the appropriateness of a model based on only its residual plot. Okay, so no pattern, it has to look random. And if you remember when we were doing these before, we had some points above and some points below, and they just kind of hopped around. That's what you want to have happen, okay? So, take a look at example 3. It's a multiple choice question. Somebody modeled a set of data with an exponential, and then they did a residual plot. What is your conclusion based on the residual plot that you see there? Somebody take a stab at it. What do you think? C. Perfect.
Good stuff.
That residual plot doesn't have a pattern. There's no, like, you look at it, there's no definite pattern there. I couldn't predict what came next. And because there's no pattern, that means the model that I chose is a good one. So whoever did this chose an exponential model. It's appropriate, no pattern. All right, let's look at example 4. You you guys took a set of data and you created a linear model and a quadratic model and an exponential model from the same set of data. That's easy to do, you just press a different button, right? So you can always do that. Now you have to decide which model was the best choice and why. Why do you think exponential, Oscar? There's no real pattern there. If you connect the dots, they're not like doing anything special, they're just kind of zigzagging all over. So definitely exponential would be the best model. All right, finally number 5. We'll go to lunch after we do number 5. Well, you got a 1 in 3 chance of guessing right. I want everybody to guess one, write down one. Write down linear, quadratic, or exponential, whichever you think is right. And we're gonna take a vote. So everybody pick one. You can't just sit there and be done, you gotta pick one. All right, let's take a count. Yeah, you got a 33% chance, right?
Yeah, I know.
Raise your hand if you said linear. Who thinks this is linear? No one?
Yeah,
I wrote it, I did write it.
Okay, so 3 of you wrote linear, okay. Raise your hand if you said quadratic. 5 or 6? All right, raise your hand if you said exponential.
I was
Back to
Every
back.
other hand better go up, right? Because everybody had to pick.
Back to back.
They don't want to be
Now,
black sheep.
why did you guys overwhelmingly think it was exponential? What was your logic? Did you have any, or were you just randomly guessing? Zaina, did you have logic? Or were you just random guessing? And it's okay either way.
I thought maybe because to find like the area of the circle, you have to do pi r squared.
So you said quadratic?
I said
Quadratic?
Yeah.
Because the whole problem is based on the area of the circle. You guys have said quadratic. I hope you had some kind of logic behind it. The whole thing, what he's doing is painting circles, and the area of circles is pi r squared, and that is quadratic. So the data points are going to be generated from a quadratic equation, so of course your model should be quadratic. Now, after he does this, he's going to buy some paint. Do you want his model to underestimate or overestimate the actual amount of paint he needs? Over. Why? So he doesn't run out, right? Now, you don't want it to be too far over, because you don't want him to have millions of gallons left over, but, it should overestimate. All right, I need you back at today, it's gotta be 35, guys, it's gotta be 35 today. 35. They're kicking us out of the lunchroom.
Each find a constant value that